Hello everyone, my name is Chang and we are Team REWARS, which is Renewable Energy and Water Resource Solutions. So in developing countries like Ethiopia and India, rural areas are still heavily populated, and people there have trouble obtaining water, especially for the purposes of irrigation due to the large amount of water required. To solve this, we wanted to develop a water pump system for wells that would be able to do this for them. But how do we power our system? Because as you can see in the following slide, about 1.3 billion people, that's a fifth of the world's population, is without electricity. In India alone, only about 55% of households in rural areas do have access to electricity. So we had to find a practical way to power our system that would be cost-efficient, reliable, and environmentally friendly. The solution? Our solar-powered water pump. Since we did not have access to a proper well, we had to develop our project on a much smaller scale. And now to describe the workings of our project, here's Marco.
So in this video, I'd like to present a walkthrough of our system as if we're out in the field. So as you can see, this is our setup. And first we would have a solar panel which converts energy from sunlight into DC electricity. Then we would have a maximum power point tracking device which will sense and analyze incoming voltages and currents using voltage and current sensors respectively. It would also control the charging of a lead-acid battery. However, we will need a buck converter to step down voltages if it's exceeding the battery's rated charging voltage. From the source, to deliver the water to its location desired, we will use a brushless DC motor water pump, and next we'll have a Hall effect sensor which will measure flow rate. Our system will be connected to a crop field's irrigation piping system to deliver the water, and finally we will have all the data obtained from the sensors transmitted wirelessly to a computer which will continuously log the incoming data. Now I'd like to introduce Jorge to talk about the benefits of having a solar pump system.
Thank you, Marco. Conventional methods of running a water pump include the power grid, diesel engines, and also solar pumps, solar water pumps. However, in rural areas like India, it is hard to connect to the power grid and also many times unreliable. Therefore, diesel engines and solar power are excellent alternatives. There are excellent benefits of using a solar pump over a diesel pump, including operational cost benefits. The graph you see in the screen came from a study conducted in Namibia, Africa in the year 2006, which showed that it was more cost efficient to install and operate a solar water pump over a diesel pump in the long run, even though the initial cost of a solar pump were much higher. Also, the study showed that the break-even point of installing and operating a solar pump in comparison to a diesel pump was 2.5 years. Not only are there operational cost benefits, but there are also environmental benefits using a solar water pump. As seen in the graph next to me, you can see the environmental impacts of using a solar water pump over a diesel pump. And the environmental impacts are less harmful using a solar pump over a diesel engine in categories such as natural resources, climate change, human health, and also ecosystem quality. Therefore, that is why solar water pumps are better application for our system. And now Gerald will talk about the overall design of our system.
All right, thank you, Jorge. So for our system design, we have three main parts. We have the charge controller, pumping system, and the data logging system. So I'm going to start in our top left at our solar panel. We're going to feed that into our charge controller, which contains the data logging controller, maximum power point tracker, and buck converter. All we're trying to do here is be efficient when transferring energy from the solar panel to the battery. Next, on the right-hand side, we have our pumping system. We're using a brushless water pump controlled by an electronic speed controller, also known as ESC. What's overseeing all of that is the master controller, which can do things like enable the pump or disable the pump if the user pumps too much water. Lastly, we have our data logging system represented by our two Wi-Fi modules at the bottom. We're going to send values such as solar panel voltage and current, the battery voltage and current, and flow rate from the water flow sensor. Now I'm going to hand it off to Ryan to talk about the maximum power point tracker.
Thank you, Gerald. So for our solar charge controller, which charges a lead-acid battery to provide power to a majority of our components, we used a maximum power point tracking device that is capable of extracting over 90% of the maximum power available from our solar panel. So why exactly would we need a maximum power point tracker with a solar panel to charge a battery? Well, in order to understand that, it's important to first understand the behavior of a solar panel. So shown on the screen are the current and power characteristics of our solar panel with respect to voltage. As you can see, the performance of our solar panel changes based on operating conditions such as cell temperature and irradiance. It's this dynamic behavior of solar panels that can cause significant fluctuations in the charging efficiency of our battery, which is something we do not want. Therefore, a maximum power point tracker is used to control the charging conditions of our battery to ensure high charging efficiency. So now let's take a look at how a maximum power point tracker does its job for our solar charge controller. Our maximum power point tracker monitors the voltages from both the solar panel and the battery in order to determine the proper current and voltage to charge our battery at. It also monitors a couple of voltage references, as well as our battery's temperature and voltage. Now, in order to accomplish all of this, we used an LT3652HV battery charger, which is the heart of our maximum power point tracker. And this charger comes with several features. It comes with a current sensing pin that allows us to tune the maximum charge current, 2 voltage references that can cause our charger to either reduce the charge current of the battery or execute an auto recharge cycle, and finally, a battery temperature monitoring pin that can cause the charger to stop charging the battery if our battery's temperature is either too high or too low. Now, in order to use these features, we included the following in our maximum power point tracker's printed circuit board design. We used a current sensing resistor to set our maximum charge current to around 2 amps, 2 voltage dividers to create our voltage references, a 10 kilo ohm thermistor to monitor our battery's temperature, and finally 2 status LEDs to indicate the current charging mode of our battery. Now, in order to test the efficiency of our maximum power point tracker, we first needed to figure out exactly how much power can we get out of our solar panel. In order to do this, we conducted the following test. We connected an electronic load to our solar panel and tuned the load impedance until we measured the highest voltage across and the highest current through the load. Afterwards, we replaced our electronic load with our lead-acid battery and connected our maximum power point tracker between the solar panel and the battery and measured the output voltage and current. And all of our values were recorded on this table as shown. As you can see, our maximum power point tracker is in fact capable of reaching an efficiency of over 90%. However, keep in mind that these are values from only one single test. For more reliable results, multiple tests are required in order to determine if this charging efficiency trend is consistent. With that said, we'll be moving on to our pumping system, and I'm going to hand it over back to Danny to talk about our choice for a water pump.
Thank you, Ryan. So when developing a water pump system, sizing the pump is very important. This depends on many factors, but some of the main ones being the depth of the well, as well as the distance the water needs to be carried to get to its destination. Now, since our system is built on a much smaller scale, we were able to use a simple centrifugal pump that uses a brushless DC motor. Now, why a brushless DC motor? Compared to AC motors, brushless motors actually have higher efficiency, and this is because AC motors have core losses within the rotor and the stator. Also, brushless motors have linear speed-torque characteristics. This makes it easier to control. Of course, high-efficiency AC systems can be designed and can be built, but such a system would be costly and highly complex. Now, in the image above, from left to right, we have a brushless motor compared to a brushed motor. Highlighted in red for the brush motor, this is actually where heat builds up due to the friction created by the brushes in the motor. This makes it so maintenance is often required. Also, the brushes create an electrical spark, which can be very dangerous. This is why brushless motors are rapidly gaining popularity throughout all different industries, from the automotive to the medical industry. And now to talk about the electronic speed controller for our system, here's Bassam.
Hi, so our electronic speed controller is a diode-incorporated IC that receives pulse width modulated signal from the master controller in addition to Hall effect sensor data from the pump, and outputs the appropriate signal to the H-bridge that will in turn the motor and the pump. The master controller also requires flow rate data to arrive and outputs the appropriate PWM to keep the flow rate constant. Because the motor is a single phase, it requires a 1 H-bridge and a constant reversal of polarity to keep it moving in a specific direction. This is half a cycle, and this is the other half. And the cycle repeats for the motor to keep going. This is the layout of our electronic speed controller. On the left, we have the sensor, the Hall effect that will be attached to the motor. In the center, we have the actual integrated circuit that will be doing the driving. The H-bridge and the pump output will be on the right. And now Sherman to talk about current and voltage sensing.
All right, thank you, Bassam. All right, so I'll be talking about the current and voltage sensing. So to do all the processing for the two sensors, we use the PIC16F18344 microcontroller by Microchip. And as far as the two sensors go, we use the ACS712 Hall effect current sensor. And then for the voltage, we use the simple voltage divider to scale down from the 12 volts available from the battery. So the PIC works by rotating two pins on the microcontroller back and forth using analog to digital conversion to gather the values from both the sensors. Once it gathers these values, it then converts them into a character array and then sends them off via UART, or Universal Asynchronous Receive and Transmit, to the Wi-Fi module in order to be able to data log the data. And now to talk about that, here's Luis.
Thank you, Sherman. As Sherman mentioned, the microcontrollers will be communicating to the Wi-Fi modules via UART. The Wi-Fi module we have used is the ESP8266, which will be in charge of two things: posting to the website and sending information to a Wi-Fi Windows application form. To post to our website, we have created a PHP file which is on the back end of the website. This PHP file will be retrieving information from the client, which will be the Wi-Fi module, using the GET method. How does this work? Simple. The Wi-Fi module will request the website with the data sensed and append it to a URL. Then the PHP will retrieve this URL, which are the last digits, and store it as variables to the website. Then the Wi-Fi module will also perform another task: send information to a Windows application form. This debugger will be displaying the voltage, the current, and the power in real time. But also, this application has the function of logging the data and saving it to the text file. This text file will be useful for us to calibrate the water pump. For example, we'll determine when it's a good time to power on the water pump, when there is enough power on the battery, or to save power whenever there is not enough sun to charge the battery. And now to talk about the cost analysis, here's Ali.
Thank you, Luis. So as a team, we want to create a system that offers efficiency and quality while maintaining to stay under the provided budget of $1,000. As a result, we spent a total of $450 on different components such as the solar panel, water pump, capacitors, diodes, PVC pipings, and so on. As you can see from our descriptive chart and table, this is how our budget was categorized. Moving on to the milestones, along to the left side, you can see a list of our goals. Along to the right, the date of completion. Finally, as we mentioned, our system is cost efficient and offers quality compared to many of the systems available today. This concludes our presentation, ladies and gentlemen. Feel free to ask us any questions. We hope you have a great evening. Thank you very much.